All right, hey guys. So I'm just going over and working through our problems and stuff like that we have for class. This is going to be over chapter 3, and then I'll make a separate video for chapter 4, and then so on and so forth. But I went ahead and started to do this in Blackboard Collaborate. For whatever reason, my connection was kind of off, so I had to use a separate recording program or whatever. This is just OBS, separate recording program, just in order to make this for you guys to see it. And then I'll probably upload it to like YouTube or whatever, and then share a link with you guys. But this is the first problem that I did before my connection went out like 3 times using Blackboard Collaborate. So instead of redoing it over again, I'll just kind of walk through it. This was a problem here. The problem wanted us to determine the magnitude, direction, and sense of the resultant for the coplanar concurrent force systems. And they wanted us to use the parallelogram law and sketch the force triangle. So this here was my force triangle. You can see I have my forces going up there, forces going that way, and then I added in these dashed lines to connect my 2 forces, which is basically if we translated this force up and translated this force to the right. And then next up, I added in my line in the center for my resultant. And then what I wanted to do was essentially, after calculating the magnitude of the resultant, which is up here at the top, took my 25 squared plus 45 squared minus 2 times 25 times 45, then a cosine of 130, which is right up here. What I want to do after that was just go ahead and my 60 degrees over here is connected to the x-axis. So in order to solve for my resultant, I could use that 60 degrees and just subtract away the amount of degrees, the angle, from that force 1 over to the resultant. So first I had to find what that theta is, that angle, which I did by solving what is called law of sines. So the 64, which is the r value, I forgot to write that up here, 64. What's it called? 64, the sine of 130 in this case. And then 45, which is my F2 value over here. And then the sine of theta. And then from there, I just went ahead and rearranged this whole entire equation to solve for theta by taking sine of -1, sine of 1, or not sine of -1, what's it called? Arc sine times the sine of 130 times 45 over 64, and I got 32.59 degrees. And then from there, like I said, I just went ahead and took the 60, and then after I took the 60, I subtracted that, or I subtracted 32.59 from it, and got a total of 27.4. So again, this is just number 1 here, and I can jump down to number 2, or not number 2, number 6. So number 6 was the next problem here, and essentially was the same thing. Determine the magnitude, direction, and sense of the problem of the resultant for the coplanar concurrent force systems, but this time we're going to use the method of components. So number 6 here, let me draw out our thing first. So we've got, of course, our y-axis, our x, and then we also have our forces here. Got the force. I like to label them, so I'll just call this F1, 75 pounds. We do have this that they gave us. This is 1, 2. Then we also have, and this is not the scale, of course, but we've got a 30-degree angle there. This is considered F2 in my case. You guys can swap yours if you wish. Since this is a what's it called, 1, 2 right triangle, we do know that the hypotenuse in this case is just basically the square root of 5. which again, that just comes from our, what's it called? So 2 squared plus 1 squared. This is what gives us 5, and then we just take the square root of that. And I get 2.24. So in case anybody does not know, square root of 5 is equal to 2.24. All right, I'm not sure if we actually need that or not, but we'll see here in a second. So where's my blue at? This is 3.6. So for r in the x direction, want to start off with that. All of my r values in the x direction. Let's see, we have negative 75 times the 2 divided by the square root of 5 plus 60 times the cosine of 30. Now again, where this is coming from, I'm going to draw this in green. Where this is coming from is, since this is in the x direction, we just basically take this force and we split it up into 2. So we can just say this force here has a, I'll just call this F2x, and also has a F2 in the y. This one here does the same exact thing. It has a downward force of F1 in the y and a leftward force of F1 in the x. So our F1 in the x is going to be F1, which is the 75, which is there. And then we have our 2 divided by square root of 5. That'll be kind of like our angle, of which it translates from that angle to the x-axis. So that's there. And we want to add in also our next Fx, which is going to be 60. So we got 60 degrees that's happening, and it's translating 30 degrees in the x direction. So that's why we do our cosine of 30. And then for this, we end up getting for Rx a total of minus 15.12 pounds. Ry, same scenario. We get negative 75 because it's going downward. And then we want to multiply this time by 1 divided by square root of 5. And of course, we want to subtract because, again, this y is going downward. So remember, our signs for our forces just goes in the direction of the force. So up here, the x was in the negative direction. So that's why we put a negative x, or negative 75. Over here, the x is going in a positive direction because F2 and the x is going positive on this way. So that's why we got a plus sign there. This one for the y direction, this is going to be F1 in the y, which is going downward. So that's why this is negative right there. And then also we're going to subtract because we have an F2 in the y direction, which is right there. And this is going to be subtracting 60 times sine of 30. And that's going to give us a value of negative 63.54 pounds. All right, so this is our x, this is our y. Now we got to figure out where exactly our resultant is. Last one. And how much it is. So r, as we know, is just equal to the square root of our fx and our fy squared, add them together. So this is going to be 15.12 squared plus minus 63.54 squared. And so therefore for R we get a total of 65.3 pounds. Now to find the angle for it, the angle in this case is going to be based on our theta x being equal to tangent -1 of the y over x so y being the 63.54 divided by the 15.12, and so therefore theta is equal to 76.6 degrees. So you might be wondering, where exactly is this located at? So I'll just go ahead and draw this here real quick. I'll draw it over here on this side. There. There. And then our resultant force in this case is going to be pulling down somewhere about here. And our theta x is going to be from the x-axis down, and the total R, is 65.3. All right, and again, this makes a bit more sense because there's more pull happening on the F1 side than it is on the F2 side, so it makes sense that it's going to pull more towards this direction. All right, so the next problem that we have is number 14. 14. And number 14 says, let me just turn to it here. Determine the resultant of the coplanar concurrent force system shown. Compute the magnitude, sense, and angle of inclination with the x-axis. Use the method of components. So the first thing you want to do, and I just want to show you guys our good old handy-dandy coordinate system here. Boom, boom, boom. Then I want to show you guys the actual forces that we have. So we got a force happening on here, which is 400 pounds. We got a force happening this way, which is 200 pounds. A force happening this way, 300 pounds. A force happening straight down. And it's nice I can actually write on these lines without having to worry about the markers getting messed up like in class. And this is going to be 100 pounds. Then I got a couple of angles to account for. This is going to be 60 degrees. This is going to be 30 degrees. And this is going to be a 45 degrees. Alright, so the first thing that we can do here, just like in the other problem, solve for our sum of the forces in the x direction. So that's going to be the R in the x direction. They're both the same there. So therefore, we have 200 cosine of 30 plus 100 cosine of 45 minus, and remember it's minus because if you have 200 in the x direction, the 200 is going to the right. In the x direction, the 100 is also going to the right. The next one, which is the 400, then that's going to the left, so that's going to the negative x direction, so that's minus 400. And we don't have to have any angle because it is along the x-axis already, so there's no angle added to it. And then lastly would be the 300, which is also negative because it's heading in the negative x direction, and it has an angle of cosine 60. And so therefore, f of x, or r in the x direction, is equal to negative 306.1, sorry, pounds. And then we do the same thing for the y direction. R in the y direction is just equal to all the sum of the forces in the y direction, which gives us a positive 200 sine of 30 minus 100 sine of 45. Remember, 100 is negative just because it's going downward. Minus 50, again, it's minus 50 because it's going downward. Minus 50 because it's going downward right here. And it's along the it's along the y-axis, so we don't have to add any angle to that. Plus 300 sine of 60. And then after I add all that up together, I get a positive 239.1 value. So since my sum of my forces are negative in the x direction, since the sum of the forces are positive in the y direction, we pretty much know, and I'll just kind of write this here, this is negative going that way, this is positive going that way. So that means our resultant r, the actual r, is going to be upwards like this. And to solve with that magnitude is going to be equal to the square root of negative 306.1 squared plus 239.1 squared, and that's going to give us a value of 38.0 degrees. And actually, that should have been in blue, sorry about that. And then for my theta in the x direction, it's going to be equal to tangent negative 1 of my y value, which is 239.1, divided by my x value, which is 306.1, and that's gonna equal to 38.0 degrees. Sorry, this is not 38.0 degrees. That is 388 pounds. Sorry about that. 388 pounds. All right, moving forward, we have number 17. And number 17 states, where's my white or gray, whatever you want to call it. This is going to be number 17. I think we might have actually done this problem in class. Number 17 just says the four forces shown have parallel lines of action. Members AB is perpendicular to the line of action of these forces. Determine the moment of each force with respect to point A, and then compute the algebraic summation of the moments with respect to point A. Be sure to note that the sense of the resultant moment. All right, so we got don't judge my horrible straight line. And then we've got a couple of forces happening here. All right, and then also, as we know, when it comes to like free body diagrams and stuff like that, we also have forces happening at our different supports, and these supports have what they call reactions to them. This one's going to be the reaction at location A in the vertical direction. This one is going to be the reaction at location A in the horizontal. And then since this is a pin support over here on the left, A is pin support, B is a roller support, so all it's going to get is a reaction at the location in the vertical direction. because it's allowed to roll left and right. So there's nothing preventing it from doing that. We do have a couple of housekeeping items. Want to make sure we've got this over here for my distance is going to be 4 feet. This one is going to be 5 feet. This is going to be 6 feet, and this is going to be 8 feet. All right. So yeah, so determine the moment of each force with respect to point A. So for this problem here, the moment at each point or each force, I would say, so the moment about A is equal to, for the 20-pound one at least. So I guess basically what they want us to do is just solve for the moment separately, and then you will solve for the total moment. So moment at A, how do I want to do? You know what? I'll do a table. I'll do a table in this case with our force, with our distance, distance CE, and then with the actual moment, what it is. The forces that we have in this case is a 20 going down, we have 40 going down, we have 50 going up, and then we've got 30 going down. The distance away from these for forces, the 20 away from A, of course, the distance away from the force, from the distance away from the force to location A or support A for 20 is going to be 4. So that's straightforward there. For the 40, it's going to be 4 plus 5, because again, we're coming from A. So that's going to be 4 plus 5, which gives us 9. Then we have 50, which again, we're coming from A. So that's going to be 4 plus 5, which is 9, plus 6, which is 15. And then we have 4 plus 5 plus 6, which is 15, plus 8 more gives us 23 for our 30-pound force there. So it's 23. And then as we know, moment is just equal to F times D, force times distance. So we can just go ahead and multiply these up. As we know, the force 20 is going downward and is causing this object to rotate clockwise. I'm just going to put this in red. This is causing us to operate clockwise. So therefore, this is going to be a negative 80 value. This one is also causing it to turn clockwise like that. So this is going to be a 40 times 9. So 9 times 4 is 36, add the 0. So we have a negative 360. 15 times 5 is 75. Add the 0, gives us 750. And let's check the directions, if it's negative or not. So 50 is going up. So when you push up here at this location at 50 and you hold it at A, it's going to rotate counterclockwise. So this is actually going to rotate that way. So therefore, this is going to remain positive. And then lastly, the 23, or not the 23, the 30-pound force times 23, which I got my calculator for that. And this is going clockwise. So that means it's going to be negative value, and it's going to be 380. And remember, the negative just comes from whether this is rotating clockwise or counterclockwise. Clockwise rotation is negative, counterclockwise rotation is positive. And so lastly, all we have to do really now is add all these up. once we add up all these moments down here, we get a negative 380. Whoops, sorry. So this is not 380, this is actually 690. I got these written down and I grabbed the wrong information. So yeah, that's 690. And then once you add all of these up, you get a total of negative 380. And that's it. That was the last part of that problem, asking us to compute the algebraic summation of the moments with respect to point A. So this would be the final answer for part B. So this is part A here. Part B, moment. All right, so next problem that we have here, that was 17. Next one is 30. So problem number 30 here. Determine the resultant and its location for the standard truck loading used in highway bridge design. The loads shown represent axle loads. So we have an image that looks like this. Boom, boom, boom. These are all resting on the ground. We've got a force happening on them here. This is 8 kips. $32 kips. $32 kips. We also have some distances on there, which is 14 feet. 14 feet. All right. So yeah, so in this case, this is a parallel force system. So we know that our sum of our forces are all going to be in the y direction, and that's going to equal to our r in this case. So it's going to be minus 8 because these are all going down. They're downward facing forces, so they're going in a negative y direction. So this is negative 8 minus 32 minus another 32 gives a total of negative 72. Then we can take our sum of our moments about A, which A let's see. Yeah, A, I'm assuming is this right here. Yeah, I want to assume this is going to be A in this case. So about A, we have the distance away from A times that force, and the rotation is going to cause. So we have our negative 32 force, and again negative, not just because it's going downward, but it's because it's causing the entire system to rotate clockwise, and that's going to be times 14 because it's 14 away from 8. And then also going to do a minus 32 times 28. So 14 plus 14 is 28. And this is going to equal to a negative 1344 kips feet. Now location of x bar, as we know, x bar is equal to m over r, which is 1344 over 72, and x bar is going to equal to 18.67 feet. So with that being said, if we were to do something like this, we would say that R, and then the distance for that is 18.67. All right, so next up is 37. We got number 37 here. And number 37 states, gotta change the page. Determine the magnitude and location of the resultant for the load system shown. Let me draw this load system here, which is a pretty funky one. Like that. And we've got a pin and a roller. Then we have this going up, down, over, down. I'm actually going to close that off just so we can kind of see these are or can be looked at as two separate. And then the last thing we have is a actual 10 kip force happening right here at this location vertically. Or not 10 kips, 10 kilonewtons. And then we have our, is that little w? Yeah, so little w, in this case here, of 7 kN over m. And then over here also, we have little w of 3 kN over m. So therefore, big W is going to equal to little w times L, which is 3 times, and I forgot to put my distances in here. This is going to be 5. This is 3. This is 6. So yeah, so this is going to be 3 times 5, which gives us a value of 15 kN, which is, you know, right in the center. I didn't put it in the center, but it's right in the center. This is big W. This is big W. I'll just call this like big W2 or something like that. And then big W number 1 is going to be equal to what is it, half base times height. So let me just double check that on my calculator here. Yeah, so this is a triangle. Area is 1/2 WL, which is was it 7, right? 7 for W, L being 6. Divide everything by 2, and you get 21. All right, so again, that's W1, that's W2. And so from there, we can now solve for our problem. So in this case, we have a total of 3 forces that are happening here. We have W1, W2, and the 10 kips. So, and these are all forces in the y direction. So it's going to be, and then they're all facing downward. Since they're forces, they're going to be negative 21 minus 15 minus 10. Which gives us a negative 46 kilonewtons. Our sum of our moments about A is going to be our 21 times 7 minus 15, 11.5 minus 10 times 14. And that's going to equal to negative 459.5 kilonewton meters. Quick note about this, again, these are negative. The 21, the 15, the 10, they're all negative just because the system rotates in a clockwise rotation when you hold it at location A. Location A is here, this is B. So when you hold it at A, you push down on those forces, it's going to rotate clockwise. Also, make sure your W1 and W2, those are in the center of your distributed loads there. So that's where I got those values from. W1, what is W1 is what, 2/3, right? I believe. And then for W2, it's going to be right and a half. So 3 plus 6, which is 9, plus 2.5 gives you 11.5. And then of course 14 for 10 kilonewtons is right there at the edge of that one. All right. And yes, so after that, we can now solve for our X bar, which again, X bar is equal to the moment over the resultant, which gives us 459.5 divided by 46. I'll make that a little bit better here. And we get 9.99 meters. All right, 56. Number 56. Let me make sure I get the right page here. Determine the resultant force for each of the coplanar concurrent force systems shown. Compute the magnitude, sense, and angle of inclination with the horizontal x-axis. Use the method of components. So 56 looks like this here. We've got the y direction, we've got the x direction, we've got our forces happening on here. I just want to make sure I grab the right picture this time, because I sure enough already made that mistake. So 150 pounds. This is going to be 75 pounds. This is going to be 250 pounds. This is going to be 200 pounds. And this is going to be 90 pounds. Then we got some angles to worry about. 45 degrees, 30 degrees, 20 degrees. And I want to say that's it. So from there, we can solve for all of our forces, of course, first. And once we solve for our forces, well, our force components, let me say that. We can solve for our force components first. And then once we solve for our force components, the total in the x, the total in the y, and we can solve for the resultant. And then once we solve for the resultant, we can get the angle. So our R in the x direction, all of our force components in the x direction is going to be 75 cosine 45. So again, 75 is right here, and it's positive in the x direction. And then how far away is it from the x axis? It's 45 degrees from the x axis. That's how we get that. Then we have a negative 250, because again, our 250 is here. It's going in the negative x direction. How far is it from the x axis? Well, it's 20 degrees from the y axis. So therefore, if you just do some quick math, 90 minus 20 gives you 70. So therefore, we have 250 cosine 70. Next, we have 200 in the x direction, which is a straight 200, no angle, so we'll just minus that. And then lastly, we have 90 in the negative x direction as well. How far is it from the x axis? It's 30 degrees, so we do 30 cosine 30. We could also do the y just as we're going through here before we actually pull out the calculator and solve for it. 75 degrees, again, this is positive, going upwards. It's going to be sine of 45 this time. And again, remember, sine of 45 is because if we make this into a triangle, the sine of 45 is opposite. So we're looking for this y direction. So it's opposite of 45, so we do sine of 45. So that's 75 sine of 45 minus 250 sine of 70 plus 150. See the 150 over there going straight up. And then we also want to plus 90 sine of 30 because there's an angle associated with that. All right, so pull out the calculator, solve for these. You get the negative 310.4 pounds for this. And then for the y direction, you get a positive 13.11 pounds. And then solving for actual r, you get the negative 310.4 squared plus 13.11 squared. And then you make sure you square root all that. You get a 311 pound force for the resultant. And then for your theta x, just like we did before in other problems, tangent -1, your y over your x, so you get 13.11 over 310.4, and that gives you 2.42 degrees. All right, so from there we can jump over here to problem number 63. Problem number 63. This problem states to calculate the moment of the forces shown with respect to point B. The forces are vertical and the member is horizontal. So this is actually a fairly simple problem. I'm just going to draw this here, just so that we have it. We've got that there, we've got that there. This is A, this is B. We have forces. We got 14 kips here. We got 25 kips here. And we got 12 kips there. And then we got point B. Or actually, so I'll make this point B. I probably shouldn't call this B also then. So I'll just call this C. um, 4 feet here, 3 feet there, 6 feet there. And to solve for this problem, again, all they're asking us to do is to calculate the moment of the forces shown with respect to point B. So that's a horrible M for moment. M for moment about B is really just going to equal to negative 12 times 3. And again, negative 12 just because this is going to make it rotate what's it called? In a clockwise direction. Sorry, skip my mind. It's 3 feet away from B, and it's going to make it rotate in a clockwise direction. So after that, we're going to have a what's it called? A positive, actually. So it's going to be positive 25 times 4. That's the next one there. It's going to make it rotate in a counterclockwise rotation. That's why it's positive. And then this upwards facing force of 14 kips is going to make this entire system rotate in the clockwise rotation. So I'm going to make that negative 14. And it looks like it's what, 10 feet away? Yeah, 10 feet, which is the 4 plus 6. I can write my feet up there. That makes it easier. And yeah, so this moment is just equal to negative 76.0 kip feet. So yeah, that's a pretty simple one there. After 63, we had 73, and then the last one was 74. So 73. What does 73 say here? So number 73 states to calculate the moments about point A and B due to the non-concurrent force system shown. Determine the location and direction of the resultant force. So first thing, I always want to do free body diagram. I mean, not free body diagram. Draw our direction diagram that they give us, just so we know what we're working with, or at least that's what I do. We haven't done too much with reactant forces yet, but so I should get, yeah, I got my red. So I've got 0.12 meganewtons. I think that's M, capital M is mega, right? 0.12 capital MN. 980 N. This is at an angle, which is going to be 8 KN. And they give us that angle, which is 40. So yeah, from there we can grab our distances here. This is 3M. This is going to be 7M, 5M, and this is just 1M. And so A says to calculate the moments about points A and B due to the non-current force system. So the moment about A is just going to equal to our negative 0.12. In this case, it's times 10 to the 6. Yeah, because that's mega. Times 1, which is the distance away from A. That's fairly straightforward there. It's, you know, the 0.12 here. And then the distance away is 1M. And it's negative because it'll make it rotate or clockwise, I should say, sorry. It makes it rotate clockwise. And then we're going to have a minus 980 times a distance away of 6. Then we're also going to minus 8 10 to the 6th power, or no, 10 to the 3rd power, sorry. It's kilonewtons, so 10 to the 3rd. And this is going to multiply by sine of 40. And then the distance away is going to be 13. So I should probably do that and that. And yeah, so MA, moment about A, is going to be equal to minus 192.7 10 to the 3rd power Newton meters. And then sum of the moments about B in this case is going to be, this time is going to be a positive value for my 0.12 times 10 to the 6. And again, that's now 15 away from B, because we're dealing from B now. And I should actually write on here, this is location A, this is location B. So this 0.12 meganewtons is 15 away. 5 plus 7 plus 3 is 15. And so wrapping up the problem here, or at least for A, we get plus 980 times 10 plus 8 times 10 to the 3rd sine of 40 times 3. And therefore the moment about B is going to be 1.825 times 10 to the 6th power. I might have to double check on this. This may actually be 10 to the 3rd power, because we have a 6th power here, we have a 3rd power there, so those should cancel out. I think I might have mixed that up a little bit there. I might have to just recalculate that on the calculator, but I'll do that later. You guys just take note of that. If you want to, you can do it on your calculator as well, but take note of that there. And this is going to be Newton meters. All right, and then from there, this is A. We also have part B. Part B just states to determine the location and direction of the resultant force. So let's first jump over to our resultant force here. The resultant in the Y, since we already know kind of a little bit more about that information, is just going to be equal to our sum of our forces in the Y. And therefore the sum of the forces in the Y direction, negative 0.12 10 to the 6 minus 980 minus 8 times 10 to the 3rd sine 40. So those are all of the forces happening in the Y direction. And then the only real force that we have happening in the x direction is what's it called? The 8 10 to the third cosine 40. So this up here is going to be equal to negative 126.1 times 10 to the third newtons, and this is just a 6.128 times 10 to the third newtons. And so to solve for R, (6.128) times 10 to the third squared. And if you guys want to round this, you probably could. So instead of 6.128, I might have even done 6.13, just so that's not 3 decimal places. 2 decimal places what I usually like to go to. So that's fine there. And then we have a minus 126.1 times 10 to the third squared. So this is only 0.1. So this is just 1 decimal place. You could probably do that same thing here, 1 decimal place, that's fine. Which I think that's what I did here, because I got 126.3 times 10 to the third newtons. And then theta x is going to be equal to 126.1 divided by the 6.128, which equals 87.2 degrees. So I'm just leaving at 6.128 just so we have the same sig figs. We got 4 on the top, 4 on the bottom. Make life a little easier. And then lastly, our x bar, I'll make the x bar over here is going to equal to sum of the moments about A there divided by our Ry, which equals to 192.7 times 10 to the third divided by 126.1 times 10 to the third. And therefore x equals 1.53 meters. So what exactly does that mean? That means if we were to actually calculate for 1 or my R, it would be like somewhere here, right? And then the distance away from A, would be 1.53 m. And the R at itself would be 126.3 kN. All right, and last but not least, we have problem number 74. And problem number 74 states to determine the magnitude of F1 and F2 shown such that the resultant of the counterclockwise couple with a moment of 220 pound-feet. So this is going to be a couple. And this couple is going to be 150 pounds with F1, F2, 100 pounds. And then our values are 4, 4, and 4. So for this problem, we know that F1 plus F2 is going to be equal to 150 plus 100, because again, we know it's a couple. So that's going to equal a total of 250 for F1 and F2 together. So F1, or really F2 as well, is just equal to 250 minus F2. We also know that if we solve for all of our moments about A, we get a total of 220, which they give us in the problem itself. They actually tell us that the moment is 220. And so we get F1 times 4 plus F2 times 8 minus 100 times 12. Again, those are just force times distance, force times distance, force times distance. So we know that F1 times 4 plus F2 times 8 is going to be equal to 1420. So that 100 times 12, bring it over to the other side. And therefore our F1 value is going to be now equal to 1420 minus 8F2 divided by 4, which is going to be 1420 minus sorry, because this is going to divide by 4 also. So we get 355 minus, these will cancel out, 2F2. So now we have F1 up here, F1 there, so we got an equation there, we got an equation there. Let's just go ahead and put these equations kind of equal to one another to solve for F2. I think the best way to do this, what is it like? Let me just make sure I did this right the first time. I think the way I did it was 250 minus F2 is equal to 355 minus 2F2. This is F. And so therefore we have 2F, geez, 2F2 minus F2 is equal to 355 minus 250. Then you can essentially just pull out some information here. You can do like F2 2 minus 1 thing, and you got just 1 F2, and then 355 minus 250. Uh, 355 minus 250 is 105. There we go. So now we know F2 in this case. We also did say that F1, remember up here, we said F1 is equal to 250 minus F2, so therefore F1 is equal to 250 minus 105, which gives us 145. and this is pounds. And they're both going up. All right, so hopefully that helps for you guys. Let me know if you have any questions on that, and then I'll be doing the next chapter.